Hi, I'm Ramya, embedded software engineer at Maplesoft Technologies. Welcome to this demo of project titled Simulating Time Passing with Manual Tick Increment using TDCI and Cortex. So in this project, we will explore how to manually adjust time delay by setting and retrieving the system tick frequency using Cortex-HAL function. So the LED toggles at regular intervals, demonstrating how time-based operation can be controlled mathematically through frequency adjustments. So let's see what is TDCA first. TDCA is Target Device Communication Interface. TDCA is used to send and receive the data between microcontroller and the host system using the serial communication. So this host is sending a command using the serial communication to the target hardware, either Cortex or Arduino, anything. So this target hardware processing the command and then return back the response data to the host via the serial communication. So this is the mechanism we are using in this TDCA. Okay, let's start with an overview of the system. The Cortex microcontroller allows us to configure the systematic frequency, which is essential for creating time delays in embedded system. The system tick is used to control the timing for delays in the project with a focus on accurately adjusting and measuring the tick frequency. The LED toggles at intervals controlled by the system tick frequency, providing a visible indication of the adjustments being made. To control time-based operations on a Cortex microcontroller by manually setting and retrieving the system tick frequency and using this to calculate precise delays in the code. This project toggles an LED connected to the particular port at regular intervals by calculating the delay based on the system tick frequency. Instead of relying on the default delay mechanism, the project sets the tick frequency manually and retrieves it to calculate time-based delays in real time. So this allows for precise control over timing operations, which is essential in real-time embedded systems. In this project, the LED toggles every 1 second because the tick frequency is set. The delay is dynamically calculated based on the tick frequency, which is why this project is a simulation of time passing in an embedded system. The real-time communication via TDCI allows the host system to monitor the project's behavior without needing to reprogram the microcontroller. This project demonstrates the core concept of time-based operation in embedded systems without relying on default delay mechanisms. It shows how to manually control the time progression using tick frequency and calculating dynamic delays based on the current tick frequency. It's simplifying debugging and testing by using TDCA for real-time feedback, and this project is particularly useful for application where precise timing is required, such as periodic task execution, sensor data processing, real-time actuator control. So by using this HAL increment delay API, so we can achieve a precise timing for various embedded applications. Let's see the components we are using here. LED, which provides a visual representation of the timing behavior turning on and off at intervals that reflect the current system tick frequency. And the microcontroller, which is Cortex, this is the core of the system responsible for controlling the system tick frequency and toggling the LED. So these are the components we are using here. Okay, now let's see this coding part. So here you should include the tdci.h header file. So this is important. Make sure you include this one to use the TDCA API calls. And inside OS application start function, so this is like a main function. In the beginning, you should call the TDCA init with your COM port number. This is the API to make the serial communication between the host and target. So don't forget to use this. and you should mention that which port and pin you going to set as output. So GPIO set output is a TDCI API call. So you should use this API to define your pin and port that you're going to use. Okay, then the following STM code. So here I'm using HAL increment tick. So instead of delay, I'm using this API to make sure the LED toggle with this increment tick API call. The system tick frequency is configured to 1 kilohertz, meaning one tick occurs every 1 millisecond. So the Hall increment tick function is called multiple times to manually increment the system tick, creating a delay. So that's why we are using a for loop. So the LED is toggled on and off. So we are using a two API, one is for on and another one is for off. So the LED going to toggle on and off with these delays, which are based on the current system tick frequency. So the LED's behavior reflect the delay intervals, showing how system tick frequency directly impact the timing of the LED. Okay, now I'm going to run this project by right click open with system editor. So here you can see the command is sent from the host side and we are getting the receive response from the target side. So you can see that the increment tick is happening and we are seeing success. So you can see A91, which means my LED is glowing. From A port 9th pin, 1 means my LED is glowing. So that command is success, and then my HAL incrementing API started running. So at the particular delay, you can see the increment tick is going on. So after this delay got finished, then you can see my LEDs goes off state. So the same pin became 0. So LED should off with the particular delay. Okay, let's see the hardware setup now. This is my hardware setup, Cortex microcontroller and LED. I gave a required connection between the board and LED. Before start the project, I make sure I'll reset the board, and now I'm going to start the project. Okay, I started running this project. So initially it will my LEDs started glowing. So my LED will toggle based on the system tick frequency. So the system tick frequency is configured to 1 kilohertz, which means one tick occurs every 1 millisecond. So the HAL tick function is called multiple times to manually increment the system tick, creating a delay. So you understand that here we are not using a HAL delay, we just doing a calculation by using a HAL increment tick function call. Without delay, we can also using this HAL increment tick API for making a tick frequency, and using that we can make a LED to toggle. So in conclusion, the project demonstrates how to configure, measure and adjust the system tick frequency using this Cortex microcontroller. So providing an accurate timing for the embedded system and controlling the system tick, we can create a precise delay. So and we can observe the impact on the behavior of peripherals like this LEDs. So this project has several important applications where accurate timing and delay management are crucial, and useful for testing and debugging systems that rely on precise timing. So these are the wider area we are using this project for making a timing control and all. So thank you for watching. So that's it. Thanks for tuning in. If you found this helpful, stay connected for more ATOS related videos. Bye.